Okay, great. So welcome to our first lecture on policy RL. Actually, a little more I wanted to cover about policy gain before we get to off policy RL. So we're going to do one more quick thing on policy gain, and then we'll get to off policy RL and actor critic and lots of fun stuff. Okay. This is another video of RL doing something moderately useful. We're learning to assemble it's called functional manipulation network. It's a very good, like, this actually something is even to have this is definitely very fixed, so it doesn't always work, but yeah, it could be useful too. Okay, so where we are in the landscape is we've kind of mostly done policy gradient. Today we're going to be talking about off policy methods or approximate dynamic programming. And next time we continue the approximate dynamic programming. Time after that we'll do model-based stuff. And so the next chunk of the class is really on going from on-policy methods like policy gradient to off-policy methods like dynamic programming or model-based stuff. And so it's like, how do we get methods that are more efficient and things that you can use on robots and so on. All right, so let's just do a quick recap. This is kind of the outline of our last lecture. We talked about natural policy gradient, how it was good because it fixes curvature problems, but it can sometimes be impractical, right? Because you have to like invert this Fisher information metric and you have to deal with step size and so on. And so we talked about this method called TRPO or trust region policy optimization. Then we talked about how the advantage function or the sum of rewards is high variance. And we talked about a few different techniques to reduce the variance of the critics really quickly. We'll go into that in more detail today. And then we talked about the God algorithm PPO, which is just clipping, right? And so we kind of try to study how to go from the conceptual formalization of policy gain to something that we'd actually use in practice. And so let's kind of go over this real quick. The three key ideas in TRPO. The first is to go from on-policy updates to import sampled updates. The second is you want to avoid huge matrix inversion, so you convert into a minimization problem for a quadratic and use conjugate gradient to solve it. And lastly, you don't want to deal with step size problems, so use backtracking line search, right? Those are three key ideas of TRPO. We talked about generalized advantage estimation, which says that you can construct different estimators for sum of reward. This is the most high variance one. This is the lowest variance one. We'll go into this in more detail, but the idea is in GAE is to do like a weighted sum of many of these estimators, and that gives you something that you might want to use with policy gradient, right? In place of sum of rewards, you can use this weighted sum of advantage estimators, and it trades off bias and variance when you choose the lambda correctly. And the last bit was about how the key intuition behind any of these methods is really to like control the amount that the policy moves. And so we can control the amount the policy moves by clipping the ratio between phi theta and phi theta I, where phi theta is your current policy. So your policy cannot move beyond some 1 minus epsilon, 1 plus epsilon ratio, right? And so been found to work extremely well empirically. The key idea is just to control how much the policy moves, but it doesn't have any second order optimization, no matrix inversion, and so on, right? And so it's nice, simple, and stable, but it maybe loses some of the nice theoretical properties that we have. Okay, so that's what we did. And today's lecture, what we're going to try and do is we're going to talk about this idea called Kronecker factorization. First, it's like a technique to make the the inverse of the Fisher information metric more manageable. It's a little bit sideways because ideally I'd like to have covered it before PPO, but we're in a bit of a rush before the discussion section. So I want to just get through that. Talk a little bit about what I think the frontier of policy gradient is. So like what are interesting research questions yet to be asked in policy gradients and like what should we think about? And then we'll talk about how we can go from Monte Carlo returns to like off policy critic estimations, things like actor critic, soft actor critic, TD3, things like that. And the second line is a typo, but we're going to talk about how to make this practical. Right? It's definitely not the same thing again. Okay. Yes, everyone with me? Good. Okay. So the idea behind this method called Kronecker factorization is really to make the Fisher information metric invertible. So we talked about PPO as a way to like avoid inverting the Fisher information metric, right? But what if we just wanted to invert it, but construct an approximation that makes this kind of tractable, right? And so what the there's this technique, it's not specific to RL, it's just more general technique for optimization that says, whenever you have natural gradients, the natural gradient type methods, right? Like pseudo second order methods, those second order methods require this inverting this Fisher information metric, which is kind of a pain. So let's try and approximate it, right? And so the issue with Fisher information metric is that imagine that you consider the Fisher information metric, which is the outer product of the gradient of the loss function with respect to the parameters, right? So the Fisher information metric, if you remember, was something like the expectation, respect to pi theta, of grad log pi theta, grad log pi theta transpose. And so each of these, let's say our parameters were d-dimensional, right? This thing is going to be d by 1. This thing is going to be 1 by d. So this whole thing is going to be d by d. Now, if you're using a huge model, let's say your model is like 10 million parameters, that's a 10 million by 10 million matrix, right? Which is really hard to invert. And so what we're going to try and do instead is trying to do some approximations which make which try to like approximate this Fisher information metric with a simpler metric, which is much easier to invert. Right? Yeah.
Not this silly question, but here like the pi theta is like, is it the or like the actual space?
It's your policy. But remember that those are likelihoods, right? Those are scalars. But the important thing is that it's a gradient with respect to theta. So those are d-dimensional because you're taking the gradient of the scalar, which is your log likelihood, with respect to theta.
So the likelihood is the one dimensional.
Yeah, so it's like this, the function you're taking the gradient off is one dimensional, and you're taking with respect to a d-dimensional theta. Yeah.
I like one thing right here, like the Fisher information metric is like some kind of approximation to Hassian.
Yeah.
So would this be like a way to approximate to Hassian without too much work?
It's a way to like butcher the Fisher information metric. So Fisher information is already an approximation to the Hessian because they ignore the second order term. This is an approximation to the Fisher information metric. So it's another. So it's even more in one direction. Okay. So the problem is if I construct this whole outer product, it's like really big and painful, right? And so what the Fisher information, what quantitative factorization called K-back, what it does is it makes it tractable with two approximations. The first is that you block diagonalize the Fisher information metric layer by layer in a neural net. And the second is you're going to like represent each block diagonal as a Kronecker product, which makes it easy to invert. So you'll cover what each of these terms mean. But essentially you can think of like, any neural net is like layer, let's just consider simple MLP, right? So you have layer after layer after layer. What they're saying is that right now the outer product of grad log p, grad log pi is going to have like d dimensions by d dimensions, right? Where each of those d dimensions includes like the cross product between layers. So let's say this was layer 1, this is layer 1. You're also going to have terms which are the cross product between layer 1 and layer 2, right? And so you're just going to say that we're going to like kill all the off diagonal terms, and we're going to approximate the Fisher information metrics by like a block diagonal approximation where we essentially pretend that different layers are intersection, right? And so what this means is that imagine that you had, this is your Fisher information metric, right? So this is layer 1, this is layer 2, this is layer 3, layer 1, layer 2, layer 3, right? You're just going to consider a Fisher information metric of this, right? And just say like all of these are 0. Yeah. And so the point is that you can like ignore the dependence between different layers. So it's like the approximation is that you're pretending that different layers are independent to each other. There's still a correlation between the parameters of a layer, but you're pretending that different layers are independent to each other, right? Approximation 1. And second approximation is that each of these individual boxes, right? You're going to like pretend or you're going to approximate it using something called this Kronecker product or tensor product, right? In a way that allows them to be invertible in a much faster way. So like we're going to try and break this into the product of two matrices, which are much smaller, and invert each of those little matrices, and that's going to let us invert a big matrix. And so the idea is like, let's consider one of these matrices as M. We're going to try and write M as like A cross B, where this is something called the Kronecker product, so that you can write M inverse as A inverse cross B inverse, right? And so the point is that A and B are going to be much smaller than M. And then you're going to like be able to invert smaller matrices in order to approximate inverse of a much bigger. Okay? And so the two key ideas you're going to do is assume independence between layers and try to express each of these blocks per layer as a Kronecker product, which allows for easy inversion. Yes, and we'll talk about what a Kronecker product is later now, but those are the two key ideas. Any questions as conceptually what we're trying to do? We're trying to say we're not going to do a D by D inversion. We're going to break it down into a much smaller inversion. That's going to make our life better. Yeah. It's just an approximation. Yeah, it just it doesn't make sense in the like overall sense, but it's like an approximation that empirically works. Like you're going to lose information. Okay, so this idea of a Kronecker product is that if I have two matrices A and B, it's kind of like, yeah.
Why is the inverted chronicle product more efficient than XQR? But you have small x essentially. What happens if I use other factorization?
Well, the whole point here is that if I have a matrix of size MA by NB, which is big, if I can reduce it into the Kronecker product of M by N, A by B, I only have to invert these two things.
No.
So that it's still much smaller than inverting the whole thing. Now there's other inversion techniques you can use. This is just one of them. This is like a particular inversion technique. Not every. Like you can use the same thing. Okay, so what the Kronecker product is that if you take two matrices A and B, right? Let's say their dimension M by N and A by B. It's kind of like a scan. So you say that the Kronecker product between A and B is that you like scan on the terms of A, and then you multiply each of those by B, right? And so you can kind of intuitively, I think of it as like sliding B along and tiling a whole matrix by like multiplying each term of A by B. Right? And so you get like, when you do the Kronecker product, you can take two matrices, this intuition maybe makes sense. You take two smaller matrices, dial them that way, so you can get a bigger matrix of dimension MA by MB.
It's like you use like lowercase a basically.
These are matrices.
I know on the previous slide you said M is
I think that was just shorthand. That should be A, capital A cross. Those are matrices. Yes, so those are capital A and capital B. So the Kronecker product takes in two matrices of dimension M by N, A by B, and essentially tiles them so that you get an MA by MB matrix, right? And so there's some nice, it's like a generalization of your tensor product, and there's some nice properties to the Kronecker product, right? And so we won't have time to derive them one by one, but let's kind of take them as given, and you guys can derive them. But the first one is that if I have the outer product of two vectors, U, V, and when I say vec, I just mean like flatten the outer product. I say if I have like, this is n by 1, this is 1 by m, this is going to give me an n by m matrix, and I want to, when I say vec, I mean like flatten it, right? You can show that that is the same as doing the Kronecker product between U and V. Yeah, so whenever you have vector UV transpose, you're going to do the Kronecker product between U and V. The product of two Kronecker products is going to be equal to AC times BT, right? So, so if I'm going to use that in the next page to derive the K factor, and then the inverse of a Kronecker product is the Kronecker product of inverse, and that's the thing that's going to make our life easier. So I'm going to say that like this is a much bigger matrix, right? Because we said that this is going to be MA by NB. This is going to be a much bigger matrix. You want to invert it, and you can convert it into a Kronecker product of much smaller matrices that you can invert, right? And so those are the three identities we're going to use. Essentially, this is just defining what a Kronecker product is. This is what happens when you multiply two Kronecker products, and this is what happens when you invert a Kronecker product. And so let's try and see how we're going to use them in our case, right? So the important thing is you have your Fisher information method, right? You are gonna you're gonna construct this as block diagonal, right? And then for each of these blocks, you're gonna write this as a Kronecker product into much smaller things. And then you're gonna say, because inverse of Kronecker product is Kronecker product of inverse, you only need to invert those much smaller. And so that's like we already talked about this. Let's try and understand what exactly this Kronecker product is going to be and how we use it for our fish information metric. Okay, so conceptually, all we're doing is we're going to make assumptions, right? The assumption is that first one is independence, layer-wise. Second one is this is not exactly equal to, like this matrix is not exactly equal to a particular Kronecker product. We're going to approximate it for invertibility. Yeah. Okay. So let's try and drive this a little bit, right? So let's say we consider any one particular layer, right? Let's call A the activation at like the previous layer, and then you multiply by W, and then it gives you S, which is the pre-activation at the next layer. Yeah. And I want to compute the like gradient of your loss function with respect to W, right? Just by chain rule, you can write this as the gradient of the loss function with respect to S times the gradient of S with respect to W, right? So you can say this is just chain rule. Yes. And now this thing is just, you just take the gradient of this thing, right? And so grad S with respect to W is just A transpose, right? And so you can say that the gradient of L with respect to W is equal to the gradient of L with respect to S. The gradient of L with respect to S times A transpose, right? Just by using chain rule, that's all we did. So remember, A is your pre-activation, or A is your activation at your previous layer, W is your weight matrix, and S is your pre-activation of the next, right? And so what this lets us say is that our gradient with respect to W is going to be equal to the gradient with respect to S times A transpose. Yes. And so what we can do then is remember our two identities from before, right? And so now this thing looks a lot like this thing, right? And so you can just say that I'm going to use this identity to express this thing as a Kronecker product, right? And then I'm going to like use this identity to write my Fisher information metric in terms of Kronecker products. Okay, so let's kind of work through that. So if you remember the definition of the Fisher information metric, it was grad log phi times grad log phi transpose taken an expectation over trajectory sample from pi theta, right? Now that's basically this term, right? Yeah. So we only care about one layer at a time because we like block diagonalized it. So we're just going to say this is my loss function, which in this case is log pi, right? We just want to take the gradient of log pi times the gradient of log pi transpose, and that's going to be the Fisher information, right? Make sense? So all I've done is I've said, this is my Fisher information metric. I'm going to try and write it as a Kronecker product thing that I can invert. Yeah. And so the first thing we're going to notice is that we can write each of these terms as grad SL A transpose and that thing transpose, right? So this vec, this thingy, right, is going to be equal to vec of this thingy, which we know from this definition is going to be equal to grad S L Kronecker product A. Yes? All we did is we used the definition. We said this thing by this logic is equal to this thing. This thing looks like UV transpose, hence it's equal to the Kronecker. Yes? And so what we've done is we've written each gradient term as a Kronecker product, right? And so now what we can do is we can write the Fisher information metrics as expectation of the Kronecker product grad SL A times grad SL transpose A transpose, right? So all we've done is I just wrote this thing as a chronicle product and this thing. Okay. So let's slow down and make sure we understand, right? So we said this is the facial information matrix, right? Just gradient and gradient transpose. Now, the gradient is equal to the outer product of the gradient of the previous layer's activations times the current activation, right? So, or the gradient of the previous layer's activation times the pre-activation. Right? That's the gradient doping. And so this is going to be S, we're going to have W, it's going to be A, or sorry, A, W, S. So, sorry, this is going to be the gradient of the likelihood with respect to the pre-activation of the next layer times the activation of the previous layer. Sorry.
There's no conservation.
No, that is like reshaping the.
What do we do?
Um,
Make dimensionality work out. Because
well,
you're writing with respect to the weight matrix will be a matrix itself. Right. And
Can you read that?
you vectorize it.
Because when you compute the facial information metric, you're like, you essentially like flatten all the parameters and you treat it as like one big parameter. Right? And so, yeah, usually when you're implementing even just like auto diff, you just like treat the whole parameter vector as a giant vector. Sure.
Just convenient.
Just convenient, yeah. Okay, so what have we done? We start with our fish information metric, and then we said each of these terms is going to be a Kronecker product. This one's going to be a Kronecker product here. This one's going to be a Kronecker product of the transpose, right? So we literally used the definition of this thingy, and then we used the definition of the Kronecker product, right? And so we said the fish information metric is a product of two Kronecker products. And we're going to use our next identity, this one, right? This one is going to be able to say, now I can convert this into a Kronecker product of these two terms instead, right? Okay. So all I did is I literally used this identity on this thing. So I said facial information metric is the product of two Kronecker products, and then you use this identity. You say this is you take individual products and then you take the Kronecker product of both. So now what we've done is we've taken my facial information metric, converted it into this thingy, right? So I'm gonna get rid of my scruff so I can, go back to some neat typeset thing. So yeah, that's all you get to do, right? So you've taken your facial information metric, written it as the outer product. Each of these outer products is replaced by this, which is a Kronecker product, and then I've used this identity to get here. Yeah.
Oh,
Yeah. Yeah, you're just styling it. And so, okay, so now what you can do is you can, you're going to make another approximation, which is going to say that now this is the expectation of a Kronecker product, and you're going to say it's the expectation of a particular product is the Kronecker product of expectations, which is like a kind of wild assumption, but it is what we're going to do. Which is we're going to say that it's like you're taking a Kronecker product and taking the expectation. We're going to say this is approximately equal to the expectation or the Kronecker product of two different expectations. And so we're going to say that this approximation says that this is going to be expectation AA transpose times expectation grad SL transpose, right? And now these two matrices are going to be much, much smaller than your initial fish information metric. And you're going to try and when you try and invert this thingy, now you can just like invert these much smaller, right? And so essentially what this thing is, like essentially what this approximation is saying is that it's assuming that this and this are independent. Right? So that's the approximation that allows you to separate it. It's kind of a crazy assumption, but it seems to work out fine. And so this is like one of those algorithms which is approximations on approximations on approximations, but like kind of works it right. But let's kind of recap. I know we went through a lot of stuff, so let's recap what we did, right? The first thing we did is we said fish information, we're gonna factorize layer wise. So we're gonna assume that layers are independent. The second thing we did is we said that the fish information for a particular block, right? So this is the fish information for a particular block. You can write it as You can write it as the Kronecker product of grad SL, or you can write it as the product of two Kronecker products, right? So you can say this times this, yes? And then you can, then the next approximation we did is that we said that the expectation of a Kronecker product is the Kronecker product of expectations, right? So expectation Kronecker product is equal to Kronecker product expectations, right? Approximation, right? But the point is then is that when I want to invert this, under this approximation, I can just invert these much smaller measures. And so that's the point of the approximation. Someone say something?
Quick question, sorry. Why did the order flip? Like, it's supposed to be like the loss with respect to gradient of loss with respect to like S like first in the bracket, but it's like A transpose in the bracket. Like, why did it
I
flip
think I might have goofed on
the
my
order?
give me 1 second. Yeah, I think I goofed on my transposes somewhere. Like, I guess you're saying that this thing, if we write this as grad SL times A transpose, then this is the Kronecker product of grad SL times A. And this is going to, next thing is going to be the grad SL times A transpose. And you can't like flip the order. So I think this has to be S cross A rather than A cross S, right? Is that what you're saying, Jingwei? Like,
Oh no, just like using the second rule, it's the grad SL term at like in front of the A transpose term
yeah, so I think
versus like the,
is expectation of grad SL transpose, Kronecker product of AA transpose instead, right? So the order is the other way. Yeah. I think that's right. Well, this one I copied from the paper. This one I did myself. And so, yeah, let me double check that I didn't get the transpose wrong. I'll get back to you guys on that. Yeah.
okay.
But I think
thanks.
what you said is correct. If we just follow logic, it should be the other way around. So it should be S cross A rather than A cross S.
Okay,
Okay.
thanks.
And the Kronecker product is actually not, it's not commutative. Because it's like a matrix product, right? You can't just like flip matrix products. So it's not. So good question, Jingwei. But I'm pretty sure I think this should be S cross. But yeah, what we did here is we made this approximation. That expectation of Kronecker product is equal to Kronecker product of expectation. This then allows us to compute these two much smaller matrices and invert them, right? And so let's see what the impact of this is in terms of like computation saving, right? So if you look at AlexNet, which is like arguably a pretty small parameter model, you have like 60 million parameters. And so efficient to make like 60 million by 60 million. Then if you do blockwise independence, you get 4 million by 4 million, still big. But then if you do the Kronecker factor, you get 4,496 by 496 and 1,000 by 1,000, right? Which is like a much smaller product. And so each of these, like now you're only inverting like these size things, which is generally a good thing to do. And so that's kind of the main point of Kronecker factorization is you made a series of approximations, blockwise approximation, approximate as the Kronecker product, and you have much smaller matrices. Yeah.
Very clever.
It seems to kind of work. It doesn't work as well as PPO, but it does seem to work. Like they use it both for like supervised learning type things and for RL, and it seems to kind of work. Like it works on Atari and so. So yeah, it's surprising. It works surprisingly well for what it is. Okay, so that's I just think this is a clever trick that you all should know about. I think it's clever and interesting. It's not what you want to use in RL, but it's clever and interesting. Yeah.
Especially with approximation. Do these have any like relation structure? If there's any like application between the approximation,
Like empirically,
or like theoretically?
I guess what you're doing is you're assuming independence in different ways, right? So like, for instance, you're like in this approximation, when you're going from here to here, right? What you're doing is you're assuming the independence of A and grad SL. So you're assuming that the activations and gradients are independent. And I guess it kind of depends on your problem and your cluster approximator to what you do this. So I don't know if we can characterize that without problem specific instance. But basically you might want to think about these are just imposing two types of independence. One is between A and grad SL, and the other one is between different layers, right? Okay, good. All right. So that is policy gradient. So yeah, that's all we're going to cover with policy gradient. Let's kind of talk about some pros and cons, right? So the pros are that it's like very simple and easy to implement. You go to your homework. That's not that far off from the state of the art. Like the distance from what you're going to implement in your homework to state of the art is pretty small. And so it's like very easy and simple to implement. It's generally stable and good in asymptotic performance, and it's compatible with huge models like the language models you use or some of the models you use for Dota were like huge image-based models. And so it's nice in that sense, and you don't actually require lots of information about the domain. Right? You just like throw a big unit and rely on lots of different sampling, and then you get like behaviors for Dota, which are pretty cool. Some simulated character control with the T-Rex, and then they also use it for things like chip design, right? I think, which is interesting. I don't know if they use it for any smart reason besides that was an easy one and stable to use. The cons are that it's extremely sample inefficient because of these variance problems that we talked about. It doesn't really reuse prior data effectively because it's on policy or close to on policy. And it's like kind of black box in the sense like it doesn't work. You're kind of, I don't know what happens. Right? And so it's like it's a little hard to like use in practice if it doesn't work. So those are generally that's my sense of like if you just want to like have a new domain, you want to use an RL algorithm, use PPO. It's just like works really well out of the box. It works great with big models. Generally, like the asymptotic performance of PPO is higher than other methods, but if you want to use it for robotics or any domain where you have limited data or you have prior data that you want to use, it's not a very effective method to use. Make sense? Okay. So here's some things that I think are, yeah. I think it is competitive. I don't think it is like AlphaGo was like clearly superior. I don't think Dota was like clearly superior, but it's competitive with the top level. Like they had this like I forgot what it's called. It's like I'm not a gamer. There was like a competition where they played against professionals and they were like competitive. I wouldn't say they were like clearly better than everyone else. Independent or something. So Go is like clearly better, and I think Dota was like a little more mixed. There's also some stuff from DeepMind on StarCraft, but that was using more of like value-based methods, not just PPO. Like OpenAI definitely used just PPO, and StarCraft and AlphaGo used more like off-policy methods, like we'll talk about. Yeah.
So this may be just a naming thing, but is PPO a policy gradient method or active gradient?
I think of it as a policy gradient method, but lots of people call it active critic. So in my mind, and this is just a naming thing, but in my mind, anything that uses Q, I think of as an off-policy method. And when it tries to approximate Q, and policy gradient always tries to approximate like a V, and like use V for variance reduction. And I think of that as still a policy gradient method. But I think lots of people call PPO an active critic method because it estimates the baseline V, and that's kind of like critic. And so I would like the way that I like to demarcate it is anything that's using like the Bellman error, etc., to learn the critic, which is a Q, the active critic, and anything that is using just a V is no critic. At least that's how I think. But I think I wouldn't say either is wrong. Okay. So what are some open challenges in policy gradients, right? So you can use these for your projects if you want. But I think people haven't really established convergence in arbitrary nonlinear settings. Like Mariam, who many of you may know, has done a bunch of work on policy gradients in LQR, LQG type settings, but I don't think it's like open in more general settings. because sample efficiency is such a big deal, often people think about how to deal with asynchronous or parallel methods to like get lots of samples quickly. So things like ISIC-GIM and ISIC-SIM and these kinds of things try to deal with that. People have tried to develop better methods for variance reduction using more structure in your problem. So like, rather than just learning this average or baseline, they try to design better baselines. That makes things more efficient. Learning from high dimensional inputs is still like a bit of a, it like works at times, but sometimes you need engineering to get there. And so there's still more research to be done there. I said it's bad at bootstrapping from prior data. I think people have tried lots of methods to make it better. But it's an open problem on how you use prior data and policy gradient methods. And then there's lots of more active research on like multi-agent policy gradient, convergence, like does it achieve equilibria? Can you use like different incentives to get better? You prove things stuff. And so I will skip the details of this so that we can get to off policy RL, but in my slides, I have like a lot of stuff in there. So you can take a look at it. Right? Okay, so I've just like listed some papers I think are interesting in each of these directions. The slides are online. Take a look at them. And I'm happy to talk about them further. Okay, good. So that is policy variant, but we want to do something that's better than policy variant, right? And so today what we're going to talk about is, can we try and reduce the variance of policy variant even further using these techniques in off-policy reinforcement learning, right? And so like the goal that I think about often is robotics, right? So how do we make policy variant a suitable tools for robotics? Well, the issue is still variance, right? So we said we have this estimator for policy variance. We like did all this sauce on top of it, but a lot of it was trying to deal with this like covariant parameterization. We did this Fisher information stuff. We subtracted a baseline, right? But we didn't really fully get rid of the variance problem, right? So the issue is that this is on policy using just the latest batch of data, which means that we have huge batch sizes, or you have like a really and you have a really high variance estimator where you just like need a ton of samples to get anything sensible out of it. So the goal of like this next section we're going to talk about is, can we develop a low variance, which means we need much smaller batch sizes, off policy, which means you can use prior data or algorithm that we can use to bootstrap from prior data and learn way more efficiently than policy data, like an order of magnitude more. Okay, so let's try and to understand how to do that. Let's try and understand where the like root of the problem is, right? So we said that the issue with policy gradient was that it's a single sample estimate, right? And what we mean by that is we're just going to use the sum of rewards in our current trajectory as a score for whether to upweight or downweight the action, right? Now, the tricky part about that is that you really want something that looks more like this, right? So in any environment where you have lots of actions in the future, you don't want to tie yourself to getting lucky or unlucky with a single sample estimate. You really want to take many different outcomes in the future when you take that action and kind of like average them to figure out how good an action is, right? And so really we want something that looks like this, which is like an average return in the future when you add a state S, take an action A, right? The tricky part is that because you're in a continuous space, you never ever get back to the same state again, which means that it's like really hard to compute this unless you can like magically reset to this state. Like if I could magically reset to this state, and I reset and I sample a bunch of times, I get a good estimate, right? Because I can reset exactly to the particular spot. But in robotics, I can't reset to anywhere, right? And in a continuous space, the likelihood of getting to the same thing is like vanishingly small, right? So how do we solve that? How do we get a thing that looks like this in a continuous space where you don't have resets? Function approximation. Right. So the key idea is that you may never get to the same state again, right? But the point is that you might get to states that are closer. And if you can get to states that are close enough, and you have a function approximator that can like understand that this state, and this state are similar, right? And kind of alias their values together. So you get an average across all of these states. Then you like bundle together the return estimate across states. And so it's not treating this, and this as completely independent. Your function approximator is giving you a way to use this return, and this return together to give you a lower variance estimate at any one state. And so the key idea in actor critic methods is to lower variance by using function approximation. And so we're just gonna say function approximation, whether it's a neural net or linear function approximator or anything else, is gonna give us a way to like compress together states. And compressing together states lets us combine, from single sample estimates to many sample estimates. That's the key idea behind actor critic methods and off policy algorithms. Yes. Okay, so what we're gonna do is we're gonna try and use function approximation to somehow reduce the variance of this single sample estimate. We did a bunch of stuff with, we did a bunch of stuff with natural gradients and so on, right? Those things are still applicable. We're gonna start with like the vanilla simple policy gradient and just deal with this term and make it low variance. You can still apply the same tricks to like precondition the gradient by the Fisher information invert, like all of those things still apply. We're just gonna try and make the vanilla gradient lower variance. Yes. Good. So we're gonna introduce a bit of notation, right? So we really want to get something which looks like the sum of rewards in the future, averaged across many different trajectories, right? So we want to take the sum of rewards going forward, average them across trajectories, and that's what we're going to call our Q function, right? Which is the expected sum of rewards in the future. You can discount them if you like. Starting from state S, taking action A on the first step, and then following a policy phi, right? And so in notation, you can say that as in state SPA, the Q function under a particular policy phi is the expected sum of rewards, starting at state ST, taking action AT, and then following policy phi. Okay? And so it's important that a Q function is specific to a particular reward and to a particular policy, right? But it's taking the first action according to something that you like choose. Let's say saying take the first action, it's like take the first action according to something that you choose and then follow your policy. Right? And so it's important that we choose this first action, it's gonna matter. Right? A value function, on the other hand, will not choose the first action, but a Q function is like, you often call it a state action value function, but it's saying you start at state S, you take action A, and then you follow the policy. Right? And you're gonna take the expectation under your policy and the environment, so it's gonna be like, this is a sum, and this is the average. And so a Q function is the expected sum of rewards in the future, starting from S and A, then following policy phi. Right? And when you want to discount it, you just add like a discount here. Right? Yes.
So is this across like the trajectory? It's a little confusing. You're in state, you take action.
Yes.
And then it's like from there it should calculate this like branching probability.
Yep.
Like all
So I haven't told you how to compute it yet. So this is just the definition of what it is. So we're gonna, like the rest of this lecture is really telling us how to compute this thing. But if we had this thing, this would kind of tell us how good as action A is at state S when you follow policy phi. Right? So it's saying that like we're going to take action A as the first step, then follow policy phi. And if I could compute this thing efficiently, then it gives me an estimate of how good it is, which is not single sample. Okay. Right. So that's the definition of a Q function. It's important, right? So remember this and go back to this slide. And we're going to try and represent our Q function with a function approximation, right? So you'll have a neural net which takes an S and A and returns a scalar. That's often what you do. But we can also approximate different things, but in this section, we're going to try and approximate the Q function. Okay. So we want to estimate, like Varun was just saying, we want to estimate, like I've just told you what this Q function is. I haven't told you how to estimate it, right? Like what is the easiest way to estimate it? Ignore the title, all the clues. But if you were to do it, how would you estimate a Q function under a particular policy phi? Just simulate a bunch of steps, right? So all you're going to do is just do Monte Carlo size, and you start at state S, or like you start at your initial state, you take a bunch of whatever trajectory samples, right? You compute the sum of rewards, and then you just try to regress, like a sum of rewards, and you just try to regress from Q to like your sum of rewards. You just do simulations. The simulation is gonna have a bunch of labels of S, A, and sum of rewards. Okay? And so you're gonna have a data set, which is S, A, sum of rewards in the future with or without discount. And then you just do a regression, right? So you just say like, your model is gonna take in S and A, and you're gonna like try and match R. Right? And so like that's what you call your Monte Carlo estimate. So you do the simple thing, you just replace your Q function with a neural net. You say the targets are just sum of rewards you got from sampling a lot, and then you just do, regression on it, right? And so you're still using function approximation. Your Qs that you're getting are not single samples; they're like averaged over many different things, right? So it's unbiased, but still might be potentially high variance because you're just like regressing. Like you might need a ton of samples to fit a Q effectively, right? And so yeah. No, you have one function approximation. Right, so you say like, actually you have like different trajectories, right? You say this is S, this is A, and I like compute the sum of rewards, right? And so for each trajectory, you compute the sum of rewards in the future. You have a data set of S, A, sum of rewards, S, A, sum of rewards, S, A, sum of rewards. Then you like stick it into an optimization of Q minus Q of SA minus the sum of rewards averaged over all SA sum of rewards sampled from your data set. Right? So the point is that you compute the sum of rewards along every trajectory. You treat those as like targets for a regression problem, and then you just do a big regression. So it's like you compute the sum of rewards per trajectory. Right? So you like take a trajectory, you take cumulative sums along the whole trajectory. That gives you sum of rewards every. Now, for every SA in the trajectory, now you have a label for what the sum of reward was that gives, right, under your policy file. And so you have like a bunch of SA pairs and like one instance of sum of reward. Right? You have a single, like in this trajectory, for instance, in this trajectory, right, I was at this state, I took this action, and then I got the sum of reward 500. In this other trajectory, I was at this other state S prime, I took this action A prime, and I got the sum of reward 200. And then I was at this other state here, S prime prime, and the sum of rewards in the future is like minus 50. Right? And so each of these are like data points for a regression problem, right? So you can think of this as like S A 500, S prime, A prime 200, S prime prime, A prime prime minus 50. And so all of them go into a regression problem, and then you like regress them.
Probably this, but why are we using this published from?
Because if it's just from images, it just depends on, you can use any architecture.
Sorry, Monte Carlo is like you do one, you start at state action SA and you roll out the whole trajectory.
You just start at your initial state, and then you just keep rolling out entire trajectory.
Okay, so it's an average over trajectory.
Yes. Well, it's not an average over trajectories because you don't know which ones are together, right? Because you can't reset, but it's more like you compute. What's your name? Pranav. Like Pranav was saying, like you compute it within a trajectory, but you like have like many such labels that come from every trajectory. And you stuff them all together into regression. Right? So in a finite horizon case, you want to do like it has to be time dependent, right? Because like the Q functions at different times, like if you reach the state S at the start versus at the end, it's going to be different. What we're typically going to do is we're going to like ignore that time dependence. You're just going to create a stationary policy. But if you want to be like completely proper about it, like this would be time dependent. Yeah.
I guess this essay from
Yes,
or
collectively.
the thought from stupid because the estimate of the 2000 would be
So remember that this is Q5, right? So this is not Q star. So this is saying how good is action A at state S when you act according to policy phi. Now if policy phi is stupid, this is going to be low.
Yeah.
Like it's not going to tell you what is optimal. We haven't gotten there yet, right? It's all that it's going to tell you is that if I was at state S, took action A and followed policy 5, even if it's a stupid agent, it's telling you how good it's going. And the answer, but it's a stupid agent, it's very bad.
Does adding a discount factor take care of the
No. Like think about it this way, right? Like imagine that you took like you had a loopy trajectory. Like this was you saw it at time step 0 and you saw it at time step like 100, right? And then you like finish your trajectory. And like the sum of rewards at 0 and 100 will be different, right? And so to Devin's point, like you really like if you're being proper in the finite horizon case, you need to make this time dependent. But the next thing we're going to discuss with bootstrapping is the infinite horizon case. So you're going to like do it with discounting and stuff. One else had a question? Yeah.
Yeah, do you have to retrain this?
So the important thing is, that's what I was going to get to in my next slide, but basically the important thing is this Q5, to train it, you need data from the current pi, right? So it's like still on policy, like you still need data from the current pi. And so every time you get a new pi, you have to retrain this Q5. That's going to make it tricky. And unlike a value function estimate, right? Like a value function estimate, like the baseline we talked about last time, it just reduces variance, it's still unbiased, right? So your value function can be wrong and it's still fine, right? But if your Q function is wrong, you're totally screwed. And so you have to be careful when you think you have to train it in. Someone else have a question? No, okay, good. So this is our first attempt, right? So obviously it's not the right one. So what might the problems be? The problems here is that you're like completely on policy, right? So like you have to collect data from pi. You're still doing regression onto the sum of a bunch of different random variables, right? You're saying that like there's reward at every time step. You're doing the sum across many different time steps, right? And so it's still like a high variance estimator. So you need a ton of data to fit QPy properly. And you're not really making use of the temporal structure of the problem, right? Like this, nowhere so far have we used the Markovian property of our setup anyway, right? Like, so we're not really making use of the fact that this is like a Markovian system. And so the issues are that it's off policy or it's on policy, sorry. It's on policy, it's high variance, and it like doesn't use temporal structure properly. Right? It's just like lumping together all of the rewards and using that for regression, right? Right. So what we want to do in our next attempt is we want to like try and have much lower variance. And we want to find a way to do it off policy and use structure, right? And so our next attempt, which is still not going to be the right one, is going to have much lower variance, learn something off policy, or we'll try to learn something. Maybe this is 2 attempts later, but we'll try to use special structure. And so the point is, like, our whole exercise now is we want to like better estimate Q. So our magic, this is single sample estimate. We want to go to like a multi-sample estimate, but we want to do so in a way that's low variance, off policy, user structure. Right? Everyone with me? Okay. So before I tell you how exactly to do it, like what are some ideas on like how we can try and reduce variance or try and do things better? Yeah. That's cool. Okay, yeah, let's try and derive that. Yeah, it's basically that, but let's try and derive it, right? So to do that, our first attempt, we're going to introduce something called a value function, right? And so a value function, V pi of SC, is basically how good is the policy pi when run from SC. So as opposed to the Q function, it is not dependent on AT, it's only dependent on SC. As the expected sum of rewards in the future when you start from SC and run your policy function. And so how is the value function related to the Q function? So that's the Q function, that's the value. Yeah. So the expectation over the Q function where you sample action from the policy, right? And so you can think of the value function as in the actor critic case, the average Q function where you sample actions from the policy. In the like Q learning case, which we'll cover next class, it's going to be like the max over. But in the active credit case, it's the average Q function, we sample actions from the policy, right? So the Q function and the value function are very closely connected. Okay, so we have this value function. You can kind of think of a value function as like R1 plus you want to discount. Right? Like something like that. There's like a sum of rewards in the future, starting at the state, adding up a bunch of rewards. Now, a natural thing we're going to use in the definition of the value function is that it has a recursive structure. And so we're going to say the following, right? So if you have a sum of rewards from T to example T, you can write this as the first reward plus sum of rewards from T plus 1 to M. You just separate out the first term from other terms. And now, what that'll allow you to do is say that this is going to be like, you can say that here also you have the expectation over policies in the future, right? So you can say that like this term internally, like, what does it look like? Like, let's say we just separated the first term and the second term, and the rest of the terms rather. Then we move this expectation on the inside as well. So you have expectation of the first reward plus expectation of all the rewards. So what does that look like? Yeah. B5 ST plus 1, right? That's it. Perfect, right? So all we're going to notice is that this is literally the definition of the value function from the next step, right? And so your value Bellman equation is going to say that you're going to have B pi of ST is equal to R of ST plus B pi of ST plus 1 taken in expectation over actions AT sampled from pi, right? And so this it's just like a recursion, right? So you're saying that like intuitively you're saying that like the value function here is equal to the reward plus the value function of the next step, right? And so as long as you're Markovian, this goes. And so if you're Markovian, that means that you can take the value function for everything in the future. Value function now is the current reward plus value function in the future, right? Okay. So we're going to follow that, and that's what we call this like Bellman equation, right? There's many different forms of the Bellman equation, but this is like arguably the simplest one. So it's like the V pi equal to the expectation under pi of R plus V pi at the next step. Yeah. Okay. Any questions about this? Okay, so now we have this recursion, right? Does this tell us how we can estimate a V pi from data? Like we want to estimate a V pi from data. I just told you this recursion works. I haven't told you how to estimate V pi, right? So we talked about estimating a Q pi by doing Monte Carlo regression. Now, how do I estimate V pi? Using this recursion. You do dynamic programming, right? But one thing we can kind of think about is we can like I spent a bunch of time on sunglasses on Bellman. This is why I spent yesterday. But if you take any transition, you have SI prime, right? You can construct a target, which is R SI AI plus V of SI prime using your current estimate of V, right? And then you can make that the target for doing like regression to match V of SI to R of SI AI plus V of SI. Right? And so essentially what you're saying is that you're trying to minimize the difference between the left-hand side and the right-hand side of this equation, right? So the left-hand side is V of SI, and the right-hand side is R of SI AI plus V of SI prime. Right? And so one recipe we could use for policy gradient is to like solve this regression, right? Solve this regression where you construct some targets, you try to do regression on V, right? Then you construct a new set of targets with the new V, try to do regression on V again, new set of targets, regression on V, new to V. This gives you your value function, V, right? And then once you have a value function, you can use that to get a better estimate of this like sum of rewards in the future. So essentially, this thing is saying, start from some V, construct targets R plus V, say V has to match R plus V. Now your V moves to V prime, construct new targets R plus V prime. Now V prime has to match R plus V prime. You get V prime prime. And so you repeat. Okay? And so the point is that you're trying to make the left and right hand side of this equation match. Yeah. And so you're gonna say, with your current value estimate, you construct targets, you try to do regression with these targets, get a new V, construct a new set of targets, try to do regression of those targets. Right? And so, it's a little, there's a little bit of subtlety here in that what I'm doing is not gradient descent, right? It's this method called fixed point iteration, right? We're not doing, I'm not literally saying take V minus R plus whatever gamma V and like do gradient descent on it. It's a little bit different than that. What I'm doing is I'm saying I'm taking my current V, constructing a set of targets, and then not passing the gradient through those targets. And so I'm saying I'm going to do V minus R plus V, but like stop gradient here. How do you write stop gradient? Right. And then you're going to try and say min with respect to V. And once I have a better V, I'm going to construct a new set of targets and then do regression on V again. A new set of targets, do regression on V again. I'll get to why we do this in a second, but mechanistically, you could think of this procedure as saying, you want to enforce this recursion. You're going to do it by constructing targets, regressing, constructing targets, regressing, constructing targets, regressing. Right? Until you get defined.
Just looking at the targets on,
Can you repeat that?
like, explain again.
The targets are, so if you look at the right-hand side of this equation, right, it's basically the current reward plus the future value. So the target at any state SI AI, you can think of it as the current reward plus the future value, right? And so it's the future value at, it's value at SI prime. If your transition is SI AI SI prime, right? Your future value is V of SI prime. Right? So your target is the current reward plus the future value. And so you're trying to make the current value as close as possible to the current reward plus the future value. Right? Which is basically what this recursion tells us. Right? That makes sense?
Where you're explaining earlier about theorem on technical gradient, you think of it as you take the reward plus the value of the next step, and then you see that as a number.
Exactly. You just treat it as a number, right? But then you like, so once you treat it as a number, you get a new V, and then you construct a new set of numbers using that updated V, right? And so you like repeat this. And so gradient descent would do something like R minus, or R V minus, gradient descent would do something like V minus R plus gamma V, minimize with respect to V, where you're passing gradients through both sides, right? That's this technique called Bellman residual minimization, which doesn't work very well. And the technique that works well is if you treat this thing as a number, right? So when I say stop gradient here, I said treat it as a number. So just a scalar, right? Or as a scale. And you like optimize for V, and then you apply the same procedure again with updated numbers from the new V, right? And you do the same procedure again with updated numbers. And you keep repeating this. Okay, yeah.
But from the definition of the G, it seems like you were to match the accurate V, you need constant concept because you're estimating what's the if you work in future within that state, and you're trying to predict that, and that state it's the average of the Q functions. So you're trying to estimate what's the future reward of that state over all transactions, and it feels like it needs.
Over action sample from your pulse.
Yeah.
And so
It's a really-
the important thing is that you're using the temporal structure. Any value estimation problem is going to have to solve that, right?
Yeah.
Like by the definition of value estimation. The thing that makes it better than just Monte Carlo, right? Monte Carlo is like, let me sample a bunch of stuff, right? I need a lot of samples because I'm like not using function approximation as my next step. So what Monte Carlo is saying is I'm just going to get a bunch of samples, I'm just going to average, which means I need a ton of samples because I'm not using function approximation as the next step. What this is saying is that like value here, we know that value here is equal to R plus the value of the next step. If you're enforcing structure on your problem. If you're enforcing structure on your problem, it becomes more efficient. So really you're using it as like temporal Markovian structure of your problem. So like your future is independent of the past given the present, right? Which means that you can say value now is reward now plus value. So that's really the trick that you're using to learn the values.
So this is about the last equation.
I'm going through it. Yeah.
So is the whole purpose of this like optimization plan that we have here just to enforce this?
Enforce Bellman consistency.
Is it like, is it guaranteed to converge?
In tabular setting.
In tabular setting?
Not in tabular settings in some linear cases, but not in general. But
Does it like,
in practice, it does okay.
it gets smaller?
Yes, yes. Like your supervised learning will kind of get smaller, but it like the guarantees that this will converge to the true V5 doesn't hold in the like non-linear. Yeah. Policy. Your current policy. Five. Five is just the parameters of your value function. So it's just saying like, is this a neural network? These are just the parameters of your neural network. So it's like your value function is a neural network that goes from the current state to a scalar, just the parameters. Yes. Okay, so yeah.
Five would be pretty much different because the rewards are just like one data point.
Mhm.
Not the ratio of So
Right.
it's not inaccurate and then you need to like really sample a lot.
Right. So often you like have to run this update for a long time to get it to convert. So this step is often called policy evaluation, right? To kind of get like how good a policy is. This is called policy improvement, which I'll talk about in a second. But you might have to run many steps of policy evaluation. But the nice thing is often you don't need policy evaluation to converge to give you a meaningful update direction for policy improvement. Right? So you don't actually need V to be perfect. Often it can be good enough. So let me get to the next step, so we can actually complete the loop and then we can have more discussion. So we estimate the value, right? So if we think of like the single sample estimate that we had earlier, we were saying, okay, we had a sum of rewards in this trajectory, right? So we say we have sum of rewards minus a V, right? And now what our Bellman update tells us is that a sum of rewards can be written as the current reward plus V at the next stage, right? So the Bellman equation says the current value is the current reward plus V at the next stage. Right, so it's saying the value function or the sum of rewards in a trajectory was like this thing was previously the sum of rewards from T prime equal to T to capital P, right? You can decompose it into the first reward plus a value function in the future. And so you can say like this term, I can now replace by R plus V of ST plus 1. Right? So you're saying that your previous policy gradient update, this whole thingy was sum R ST AT minus V of ST, right? So this T prime, T prime. So it's the sum of rewards in the future minus the current value function or your baseline. All we're saying is that the sum of rewards in the future can be thought of as the current reward plus the value function. So we're saying that this is going to give us R ST80 plus V ST plus 1. Right? And so what we've done here is that we've not said it's no longer a single sample estimate because your value function is trained across everything. Right? And so your value function can potentially see lots of states in the future, not just literally the one in your trajectory, right? So if we go back to our the figure we had back here, right? What we're saying is that this thingy is the sum of reward R ST prime AT prime from T prime equal to T to capital T. Right? It's literally the sum of rewards in this trajectory. Yes. What this thing is saying now, our new update for this is R of ST AT plus V of ST plus 1. And so it's saying the reward here is equal to the first reward plus like the V of all the things in the future. Right. So it's saying you're not doing a single sample estimate anymore because your value function is trained across lots of stuff, right? So if you see 1S here, 1S here, 1S here, your function approximation is no longer a single, it's like no longer a single sample estimate for that trajectory. It's like average across lots, right? And so what we've done is we've converted this single sample estimate to like, a function of like, this is what you call a bootstrap estimate. And so the point here is that you've kind of realized this goal of trying to do function approximation across states by saying that your value function is going to capture this, like, it's going to take in S, so it's going to put similar S's close together. And so as compared to that thing, which just sounds along your current trajectory, your value function is going to average across trajectories. Okay, does this parse? If it, I'm sensing some confusion. So if there's confusion, let's talk about it now. Otherwise, the next lecture is going to be a blur. Yeah.
So, what's the next slide where you come up with the.
You want me to do value function estimation or something?
Not important, future, yeah, that one. So here, the V's at the end of the last equation, should those be like V, like phi, I?
Yeah.
Uh,
So these are like V5.
and then here, like this RST is AT plus V phi pi, is that also the Q? Like, is that?
Yeah, that's an approximation. And we'll talk next about how to directly approximate the Q.
Okay.
We're currently trying to approximate it. Right, so this update is going to approximate a V using dynamic programming. And it's going to use the V, so it's going to do one step look at that for the V to give you something that approximates the Q. Right, and then this is what your baseline. So this is, you can think of this as rewards in the future. This is your average reward baseline. Is an approximation.
Yeah, but I guess, the first equation, let's talk about first, the bottom one, are those.
Like this thingy. This is an approximation. This is an approximation to this.
And then on top of that, there's like the subtracting the value.
Yeah, you can always subtract the value because we said it was like unbiased, right? You can always subtract the value. Because it doesn't change the.
And I guess one more question, like, why is this like, the bottom thing an approximation to something?
If your V is not perfect. Okay, like if your V was perfect, then.
Phi is outputted by the neural net.
Well, phi is the neural net. Like V is a neural net that maps from S to a scalar.
But I guess like, can we just like, when we run multiple simulations, can we just like have two like neural nets that alternate?
We do that in practice, but they're for very specific reasons. So help me understand why you think that might be it. And I'll tell you if that's the reason.
Cause like, you just like need to like, otherwise it would be too diverge so much.
I don't think, like, the point is that this thing will usually, like, the reasons you use it often is to deal with overestimation. Sometimes you're overly optimistic. But like this thing typically converges pretty well, right? So all this is saying is it's just trying to enforce. It's like, it's not a divergent procedure. Usually like in theory, it's divergent, but in practice, it's often very, very stable. Not very stable, it like often works. But like basically, it's just like, you can think of it as like, you're constructing targets, you're doing regression. You're constructing targets, you're doing regression, right? So this thing is going to converge to something. When it's converged to something good enough, you do a policy get that. But you don't need to keep sampling for this. You just can use a fixed, you can keep doing this procedure on a fixed set of data. So you take a set of data, you keep constructing targets, do this constructing targets, do this regression a bunch of times, so you get a peak. And then you do the policy grid to get a new part, and then you get new data. Okay, so if we try to think about how this falls into the whole landscape of things, right? We've taken our policy grid update, which like had a sum of rewards. And we said, now we're going to replace this sum of rewards by a lower variance estimate, which is like this thing, right? R plus next value minus the current value. So don't even worry about the minus the current value, that's just to reduce variance, but you can just think of this as you're replacing sum of R by R plus the next value, right? And so that's using function approximation to reduce variance. Yeah.
Are you training V?
Yeah, so you like iterate between these two steps. So I was just gonna actually walk you through the steps here, right? So the way you do this is you collect a bunch of data, then you're gonna fit a value function on policy data. So you said, I collected data from 5, and then I fit a value function V by doing the procedure I mentioned earlier. So you try to optimize for the parameters 5 of your value function V. So that's what you're gonna call policy evaluation, right? And so policy evaluation is going to give you a good V. Once you have a good V, you're going to then try and do the policy gradient. Right, so you computed V with on the data that you have. Then you're going to do policy gradient to improve your policy using that. And then you're going to collect more data. Right? And so you're going to collect more data. Sorry. You're going to collect more data and then you're going to repeat, right? And so there's like policy evaluation, policy improvement, data collection, policy evaluation, improvement, data collection. And so you go in the loop. You do it, you can think of this as telling you how good is my policy. This is saying use my estimate of how good my policy is to reduce the variance of policy gradient, improve your policy, collect more data, re-estimate how good my policy is. Does that make sense? Okay. So that's the procedure. Why might this be, so like, why might this be good? What is the advantage of doing it? It's more complicated. I have another thing that I have to do. Why might it be good? Reduce variance, exactly, right? Reduces variance, which is good. But why is it still, why doesn't it, if you remember the like criteria we talked about, right? We want these three criteria. We want lower variance, which check mark, right? We want to use temporal structure, check mark. But is it off policy? No, right? And so the problem is that if you're trying to use this update for doing your policy, learning your value function, right? You have to do it on data sample from pi. You can't do it on other data. And so the problem with this update right now is that it's still on policy, which means that I still have to collect, yes, it reduces variance, but let's say I have like 100 iterations of training, I can still only use the 100th iteration of data. And so it's still on policy. And so the issue is that it is on policy and we need to develop an off policy method to be really efficient, right? Now, as an off policy, you can use data from prior iterations, it can use data from prior experiments, it can use data from others. And so you want something that doesn't just rely on data from pi, like we don't want this condition, right? We want data from arbitrary other sources. So what we're going to do, I mean, we're out of time, but you can check time. Is that we try to construct an algorithm that tries to reduce variance, use structure, and use data from .pi. Yeah. One last thing that I wanted to touch on before we end is that this, if you remember from last time, we talked about this idea called generalized advantage estimation, which I ran through like at hyperspeed. I think we can revisit it. And Ethan, you might have asked a question on LSTEM about it, but let's think about this in the context of like what we just discussed, right? So what we just discussed is we discussed this value-Bellman equation, which says that, you know, we discussed the value-Bellman equation, which says V pi is R plus V pi next, right? And if you want to like do with discount, it's going to be R plus gamma V pi next. Now you could also do alternative versions of this recursion where it's V pi is equal to R plus R, like R of ST plus R of ST plus 1 plus gamma V pi ST plus 2, right? You can just like push the recursion out further and further and further. And so if we revisit this like generalized advantage estimation idea, you can say that this is literally the Bellman equation, right? We just wrote this out. R plus gamma V minus V. You can also push it out further. You can say it's R1 plus gamma R2 plus gamma square V minus V. And you can like take this to the extreme where it's R1 plus gamma R2 plus gamma square R3 to the gamma to the n minus 1 Rn. So you can just keep pushing the recursion further and further and further. And this is back to our Monte Carlo estimate, right? This is just like, imagine you took all the samples and you didn't use any function approximation. So this is our Monte Carlo estimate, high variance. This is our value function estimate, which is low variance. But if the V is wrong, this is like screw, right? And so this is bias, high bias. And this is high variance, right? So we have a trade-off between things that are high bias and things that are high variance. And the whole idea of GAE is really to just like average these estimates. So that in the like high data regime, like this thing will be fine. in the low data regime, often this thing is better, right? And so often you're gonna like use different lambda to like trade these things off. But this is coming from the Bellman equation, right? It's just saying that the current reward is R plus gamma times the next sum of rewards. This is R1 plus gamma R2 plus gamma squared, the next sum of rewards. And so you can like kind of interpolate between them. Right. So the main point I want to make is that we can rederive all the stuff we did for GAE from the perspective of the Bellman equation, where the Bellman equation is literally just saying value at state S is equal to R plus gamma times value at the next. Okay, thank you. I appreciate it. Thanks.